Alright, we are back. This is going to be chapter 13, and this will be our second video in the installment for NMR spectroscopy. Alright, kind of looking at a worked example problem here. Lastly, on our last video at the end, or a large portion of the end of the video, we talked a lot about how the environment can affect where our peaks would be. So kind of a look at how environment can play a role in terms of what's bound and where it is in our structure. This worked example is a good illustration of that. So here we see the question states, explain why 2-cyclopropene shows signals for 3 kinds of protons in proton NMR. So to kind of understand that, the first thing you want to do is you want to look at the structure of 2-chloropropene. So when we look at 2-chloropropene, we're looking at something kind of like this: 1, 2, 3, right? 3 carbons. You've got a double bond in there, and then you have a chlorine at the second carbon position. So this is 2-chloropropene, and if you notice, you have this carbon that has 3 hydrogens, and then you have this carbon that has 2. But the question is, all right, so why is it not 2 signals instead of 3? And one of the ways to kind of understand this whole environment affecting where our signals would be, or how many different signals we have, you actually want to look at this structure in the realm of a Newman projection. So when we look at the Newman projection, this would be my dot, that would be my circle carbon. All right, and so between the dot and the circle there is that pi bond, and you notice what winds up happening here. You have a hydrogen and a chlorine that are on the same side, right? Both of these are on the top. So if you imagine this is that pi bond kind of acts as this is the top of the molecule, this side's the top, this side's the bottom, right? You're noticing that you're going to see this hydrogen is eclipsed with the chlorine, as we see here in the Newman projection, and then this hydrogen is eclipsed with the methyl, as we see up here. And so because these are eclipsed, we know that eclipsing interactions can have significant energy associated with them. We are also going to see that these eclipsing interactions can affect the shielding and de-shielding of a given hydrogen. So that's why having these 2 different eclipsing interactions, these 2 hydrogens are distinct from one another. So this would be 1 signal, this would be a second, while all of these 3 here would be our 3rd signal. So we have 1, 2, 3 signals based off of environment and bonding nature. Okay, so that's something to kind of keep in mind, and we'll even talk about how these could look possibly in an NMR spectra in the future in continuing slides. But this is going to be a little bit more of a hassle because we have to introduce splitting and all that stuff, which we're about to get into. All right, so one other thing that you want to pay attention to in our spectrum is that we'll have something called integration. And so for anyone who is taken Cal, I think it's brought up in Cal 2, I don't know what it is here at State, but it's either in Cal 2 or Cal 3. You talk about integration of a curve, integrals, and so if you're doing an integration, what you're doing is you're actually looking at the area under the curve, and so we as chemists use that concept quite frequently in our spectra, because if we integrate under a given peak, finding the area under the curve, under the peak, that can actually give us an idea of how many, like what concentration we're looking at, or what how many hydrogens we're talking about. So when we talk about integration for NMR, we're talking about how many hydrogens or what ratio of hydrogens we're looking at. So a couple of ways that we could see integration, if we look at this structure here, our ester that we have here, you see that we have, based off of symmetry in our molecule, we have 1, 2, 3 methyl groups, but all of these hydrogens are pretty much the same based off of symmetry. And then we have a second set of hydrogens over here that are distinctive. So we should only see 2 different signals in our NMR spectrum. And if you notice, there's a difference in height, but also the slides that you have show it a little bit better. I've already written on it, but there is this weird little zigzaggy line that's drawn, and that's called stepwise integration. And so what that does is it actually compares the ratio of hydrogens. So if you were to take from flat part to flat part, you'd see you have that distance. And then this being the bigger one, how many times would this length right here from flat to flat, how many times would that fit in this flat part to flat part? And so if you notice, I've already shown you it's 1, 2, 3. So you see that you have 3 times as many of these types of hydrogens as you do these, which makes sense, right? You have 3, 6, 9 of these hydrogens, and you have 3 of those. So it's a 1 to 3 ratio. Another way you could see this integration is where we actually give you the number of hydrogens. So this peak corresponds to 9 hydrogens. This peak, that signal comes from 3 hydrogens. Okay, so those are a couple of ways that we could see this integration, right? And that's going to help you tremendously when it's given. It's going to help you tremendously in figuring out how much symmetry you have, and a lot of other structurally important features. All right. And so looking at another worked example we have here, it says mention the number of peaks for proton NMR for 1,4-dimethylbenzene. All right, so here I've given you like a nice clean structure for 1,4-dimethylbenzene. And what we see is in our NMR spectra, we have 2 peaks, 2 signals. Let me say that, 2 signals. And so what we see, this tells us that we really only have 2 different types of hydrogens. And so specifically, when we look at me drawing that 1,4-dimethylbenzene, you can see that I actually have 2 planes of symmetry in my molecule. I have one where I can cut through the bonds in the benzene here, or I can cut along these carbon-carbon bonds for our methyl groups coming off the benzene. So I have 2 planes of symmetry. And what does that tell me? Well, that tells me that based off of this plane of symmetry here, that this hydrogen and this hydrogen are the same, so HA, HA. But it also tells me these methyl hydrogens are the same, so B, B. And then it told me that these 2 were the same. However, you notice these also say HA because I had a second plane of symmetry here, which told me that, oh, well, these 2 from the other plane of symmetry were the same. Now these 2 are the same. So really, I have 1 signal based off my benzene hydrogens, and I have 1 signal based off my methyl groups coming off of the benzene. Okay, and so as I said before, benzene is a very distinctive. The hydrogens on benzene are very distinctive. We see them quite frequently somewhere in the 6.5 to 8.5 region, and so that's what we see there. And then here are methyl hydrogens. This carbon is attached to a benzene ring, so they're not really in that aliphatic or alkane region. They're pushed out more because you are seeing, if you recall, these hydrogens based off the double single bond, those do look like allylic hydrogens, and so that kind of falls in that region. All right, so there's an example there. Oh, sorry, and then lastly, we need to look at integration here. You notice how the benzene hydrogen peak is smaller, lower than our CH3 hydrogen peaks. And that's because, well, if we go back and look, right, you have 3, 6, you have 6 methyl hydrogens, and you have 4 benzene hydrogens that are equivalent, right? So you have a 6-to-4 ratio, but that could be simplified to a 3-to-2 ratio. So that's why we see this should be, this peak, should be roughly a third taller, or have a third more area under the curve than this peak, right? So that's why it's taller. All right. All right. Also, something else that you need to get familiar with seeing in your NMR proton NMR spectra would be what's called splitting, spin-spin splitting. And so we've seen previously, like the peaks that we have here, they look like just lone solitary peaks, right? And we call those singlets. It's one peak. All right, but what's going to wind up happening is you'll actually not just get what's called singlets as signals. You'll get doublets, triplets, quartets, quintets, so on and so forth. And so a singlet, as we've seen, looks more like this, right? Forgive my artistic talent. I know it's just spectacular, and you're going to be envious of my skills. A doublet is going to look more like this. All right, so two kind of peaks right next to each other. A triplet, hang on, let me draw an arrow. And then a triplet is going to look something like this. Okay, so you see 1, 2, 3. Quartet, quintet, so on and so forth. So looking at what a quartet could look like. All right, and then a quintet. 1, 2, 3, 4, 5. All right. Now, and something that I do want to draw your attention to here in our doublet, triplet, quartet, quintet, right? You see the ratio of intensities here. You notice that there's some symmetry here, right? In a doublet, those two peaks are approximately the same height. In a triplet, you have three peaks where these on the extreme ends are the same height, while the one in the middle is taller. And you see that kind of keeps going on as we move to more and more. So go into quartets and quintets, right? These two on the end are smaller, the same height. The two in the middle are taller, the same height, right? Quintet, see the symmetry yet again? It just kind of does this, kind of looks symmetric, right? Has symmetry about it. All right, so that's something that I do want to kind of have you notice, especially in the future when we talk about weird things that can happen based off of our environment. Okay. All right. So these are the types of splitting that we're going to see. Now, where does these splitting patterns arrive from? Well, the hydrogens that give us these signals, they're going to give us splitting based off of how many neighbors they have. So we're going to be using what's called the N+1 rule. Okay, so N is the number of equivalent neighbors that a given hydrogen would have. Okay, there's also this coupling constant, which talks about the distance between peaks. I don't want you to really worry about the coupling constant or anything. That's something that's a little beyond, because you notice here it gives you a specific value, 7 hertz. Don't worry about that. Really, I want you to become quite proficient at this N+1 rule. All right, and it sounds like it seems like it might be hard, but as we do some examples, I think this will make a lot more sense. All right, so in our N+1 rule, right, we want to look at some examples here. All right, so if we look here at 2-bromo propane, for our 2-bromo propane, based off of symmetry in the molecule, right, here's a condensed looking structure, but I also drew the skeletal structure. You can see here how you have 1, 2, 3 carbons, right, and then you've got a bromine in the middle. So based off of symmetry, right, you actually can see a plane of symmetry here where these hydrogens on the ends are equivalent based off of symmetry, and then this one in the middle is off by its lonesome. It's an individual, right? It's a lone wolf, a wolf pack of one. All right, so anyway, when we look at that, that's why we're going to see only 2 different sets of signals. All right, now you notice here we have a doublet, and then we also have, I want to call that a quintet, but I'm pretty sure that is a septet. Wait, 1, 2, 3, 4, 5, 6, 7. Yeah, I'm pretty sure that's a septet. All right. So, but when we look, why do we get 2 peaks here and then this 7 weirdo peak-looking stuff here? All right. Well, let's look at the neighbors. Right. So if we look at our A hydrogens, all right. So we have 4A. You have CH3 here. Right, so those are your A hydrogens. Now, what you want to do is you want to look at their neighbors. So imagine, if you would, carbons are the houses, and hydrogens are the people that live in the houses, right? So you want to go down the street to the next carbon, to the next house. How many hydrogen neighbors live in that house? Only 1. So when you look at the A hydrogens here, they have 1 neighbor. So remember, it's N+1, so the A hydrogen should give you, right, N+1, which would be 1+1, so you should see 2 peaks, or a doublet, right? And that's the same thing over here, right? You have a CH3 here, right? So the carbon is the house, so go to the neighboring house, right? It has 1 hydrogen neighbor, so, right, equivalent, you have 2, you get 2 peaks. So the A hydrogens are what give you the doublet. Okay, now, when you look at this middle hydrogen, because we've done those now, those are our doublets. Okay, when we look at the B hydrogen now, right, that hydrogen lives in this house, that carbon. And if you notice, though, it has 2 houses that neighbor it. It has a carbon to the right and a carbon to the left. So when you look, there are 3 hydrogens here. So there are 3 neighbors on that side. So N equals 3 on that side. But then also going to the left, you see another 3 neighbors. So you actually, for HB, your N plus 1 is going to be 6 plus 1, or 7. And so that's why you see that septet right there. All right, so HB is what gives you the septet. Okay, and yet again, notice the symmetry here. Okay. All right. All right, and so the one thing that I do want to talk about is this multiplet. And so technically, all of these could be considered multiplets, having a doublet, a triplet, a quartet, quintet, right? Because it's more than one peak, so it's multiple peaks, or this spin-spin splitting. But anytime that you see me use the label multiplet, it's kind of a hint to you that something crazy is happening. Okay, so for example, in this scenario, I would have told you that, like if I said something, I would have told you that that's a doublet, right? And I would have told you that that was a septet, right? Vice versa, looking at this, I would have told you, okay, well that's a quartet, that's a triplet. Okay. However, when we go and look at something weird, if we look at this weird splitting here, I would have called that or labeled that as a multiplet. And what that is you're actually seeing 2 different signals. They're not resolved from one another. They're actually very close in their frequency where you see them. For instance, right, 1.77 ppm versus 1.71 ppm. This set of peaks right here is actually 2 different signals that are really close to one another. Okay, so I would label that a multiplet to kind of give you that idea that, oh, we've got 2 signals that are really close to one another. And so in particular, when we look at C, right, the 2 hydrogens that are here, right, they have how many hydrogen neighbors? They've got 3 at this carbon, and they've got 1 at that carbon. So they have a total of 4 neighbors. So you see it's 4 plus 1, which gives you a quintet, right? When you look at these 3 hydrogens at this carbon, they only have 1 neighbor. So you're looking at 1 plus 1, which gives you that doublet. Okay, and so these 2 are very close in frequency, and they kind of overlap. And you would think, oh, okay, well, when I see that multiplet, then it should be 5, 6, 7. But if you look, you actually have 1, 2, 3, 4, 5, 6. You only see 6. These overlap, so I wouldn't say perfectly, but they overlap well enough to where one of your quintets peaks and one of your doublet peaks are at the exact same frequency, and so you don't see 7, you see 6. But that multiplet is a big red flag or flashing light, neon sign telling you, hey, something weird's going on. We have multiple sets of hydrogens that are similar. They're not equivalent, but they're similar. So you could see 2 different signals really close to one another. And the other thing that kind of stands out here in this multiplet, if you notice how you have 2 tall peaks, and then you've got these other 4 peaks that aren't, there's no symmetry. If you compare all of these peaks, they're not symmetrical. So if this were, say, not a multiplet, but a 1, 2, 3, 4, 5, 6, a sextet. So if they were supposed to be a sextet, which means you'd have 6 peaks, a sextet would actually have symmetry. So you would see 1, 2, 3, 4, 5, 6, right? So you would have symmetry. The 2 on the ends are about the same height, the next 2 are the same height, and then the 2 in the middle are the same height. Here you don't see that, right? These 2 are tall, and then you see this kind of similar, these 3 are similar, and then that one's really small. So you don't see that symmetry. See here in that sextet, right, 1, 2, 3, 4, 5, 6, see how you have that symmetry that's very similar to that? So that is telling you that these hydrogens that are giving you that signal, they have 5 neighbors. And so that's when we look at B, the hydrogen that's here, right? It's got 3 neighbors here, and it's got 2 neighbors here, so a total of 5 neighbors. So that's why we see the sextet there. All right, so multiplets. If you see the word multiplet, something weird's going on. Pay attention. All right. All right. So I'm going to stop this video here to allow you time to kind of process.